Well, uh, you see, on nights like this, when the sky feels a little too quiet, I sometimes find myself wondering about the things that slip through that darkness unnoticed. And, um, well, maybe you felt it too, that gentle tug of curiosity that makes you look up and ask a simple question, a small question that grows larger the longer you hold it. What if the universe is sending us messages in the form of wandering fragments of ice and dust, tiny travelers that uh, tiny travelers that arrive without warning, carrying stories older than the sun itself? Imagine it with me. A telescope sweeps across the sky in the stillness of late night, and suddenly there it is, a faint smudge of light drifting with a kind of restless determination. First it was 3i Atlas, and then in the early months of 2025, another visitor appeared, K1 ATLAS, moving through our solar system as if it were following some ancient trail. Two objects, two wanderers separated by vast distances, yet somehow stirring the same quiet unease among astronomers. It's not just coincidence, it's something that feels like an echo. And that's the thing. On the night K1 was being watched like any ordinary comet, it didn't behave. It broke apart days after surviving the most intense moment of its journey near the Sunday. Not the moment of greatest strain, but after, as though it were waiting, as though it were choosing its moment. And that makes you wonder what these visitors truly are. Not just what they're made of, but also what hidden mechanisms guide their paths, whether it exists at all in the way we think. So when we talk about these objects, we're not just looking out there, we're also looking in here, into our own understanding of how fragile our assumptions can be. And maybe that's why they unsettle us. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. Well, let's return to that quiet corner of the cosmos where K1 ATLAS first drifted into our awareness, because this is where the story truly begins to breathe. You see, when astronomers spotted it in late May of 2025, they logged it almost absent-mindedly, as if it were just another icy wanderer from the Oort cloud. And that makes sense, because most comets that come from that distant reservoir behave in ways we've grown familiar with. They arrive on long stretched orbits, they warm up, they shed dust, they glow. Nothing unexpected, nothing unsettling, nothing that asks us to rethink how fragile these frozen relics really are. But K1 was different, and in ways that became clearer only as time moved on, slowly at first, then all at once. So the comet was catalogued as one of those long-period visitors, its orbit dropping toward the sun with an elegance that felt almost scripted. And the early models predicted everything would be neat and tidy. It would swoop in, survive if it was sturdy, disintegrate if it was weak. The universe, in that sense, offers simple choices. But as K1 headed inward toward perihelion, toward that razor-thin distance of about 0.334 astronomical units, astronomers were quietly holding their breath. Because, we understand that the inner solar system is no gentle place for a comet. The sunlight isn't just warm, it is brutal. The radiation strikes, the surface cracks, the interior bakes, and the tidal forces tug and twist at the nucleus. If a comet is fragile, it shows it there at the point of closest approach. It's not some dramatic explosion, not always. Sometimes it's a gentle unspooling, as if the comet is sighing apart. But either way, it usually happens right then, right at that moment of deepest stress. But K1 did something that didn't match the script. It held together. It slipped past the sun, emerged from perihelion intact, and that in itself was already a curious thing. Because fragile comets do not usually survive such a close encounter, but sturdy ones do, and everything seemed to point toward K1 being sturdy. So the astronomers relaxed, perhaps only slightly, perhaps only for a moment. They followed it across the sky, expecting a normal decline in brightness, a normal tail, a normal journey outward again. And, well, that expectation didn't last long. You see, a few days after perihelion, when K1 should have been settling down after its fiery descent, something else happened. And it happened quietly at first. A slight change in brightness, a distortion, a softening of the nucleus. And then, as images rolled in from the virtual telescope and other observatories, the truth emerged with a kind of slow dread. The comet had shattered, not at the moment of greatest pressure, but afterward, as though it had been holding a secret, as though it had carried stress deep within and released it only when the sun was already behind it. This delayed breakup was not expected. It's not what fragile comets do, and it's not what sturdy comets do. It's something else entirely. Well, if you imagine standing beside one of those telescopes on the evening of the 12th of November, you'd see it plainly. The nucleus was no longer a single coherent point of light, but a procession of fragments moving in a strangely organized way. The lead fragment glowed brightest, dragging behind it a luminous stream of dust like a headlight beam stretching into the void. And behind it came the others, each with its own little coma, each a pale echo of the original body. They were not chaotic, not scattered randomly, but arranged with an odd sense of structure, a spacing that felt too even, too deliberate for a simple mechanical breakup. And, well, that's what unsettled the astronomers first. Not just the fragmentation, but the way the fragments behaved. It's not just that they separated, it's that they separated with purpose. That feeling of choreography, of pieces moving in a coordinated line, suggested forces at play beyond the usual stresses of heat and rotation. A typical disintegration leaves a cloud of debris, a foggy smear with no clear shape. But K1 was crisp, structured, almost architectural, and the more they studied the images, the more puzzling it became. So why did K1 wait? Why didn't it crumble at the moment of maximum pressure? Why break days later when the worst was already over? You see, this is where the scientific mind hesitates, draws a breath, and begins to question every assumption. If the nucleus had internal layers, maybe those layers held tension that didn't release immediately. Or perhaps volatiles trapped deep inside needed time for heat to seep through, time for pressure to build. But even then, the pattern of breakup doesn't fully match that explanation. And when you think about the physics of comets, you think about heat flow, fracture propagation, the sublimation of ices, the way pockets of gas can carve channels through rock and dust. You picture a kind of slow internal weather, a microclimate of pressure and temperature. If any of that were off balance within K1, perhaps that explains part of what happened, but it doesn't explain the timing neatly. It doesn't explain the clean line of fragments. It doesn't explain the brightness jet beneath the lead piece. It's not that scientists don't have ideas, it's that every idea fits only part of the puzzle. And puzzles like this, well, they have a way of pulling you in. They have a way of making you look again, look deeper, question whether the simple stories we tell about comets are too simple after all. Because comets are relics, they are time capsules. They are frozen memories of the early solar system. And when they break apart, they reveal something of their history, their structure, their hidden past. But K1 revealed too much and too strangely. The deeper astronomers looked, the more they realized that this was no ordinary breakup. The spacing of the fragments hinted at rotation, but rotation alone couldn't explain the sustained brightness of the jet under the lead fragment. That detail suggested a source of gas that remained active even after the nucleus had fractured. It suggested outgassing from a relatively fresh surface, something newly exposed. And that means the breakup was not a gentle peel, but a sudden tearing of layers that exposed material not seen for billions of years. And that scent of the ancient world, well, it draws scientists like moths to a flame. Because what if the comet wasn't as simple as we assumed? What if its structure was layered in ways that defy the standard models? Not just porous, not just fragile, but complex. Maybe it was a rubble pile, a collection of loosely bound boulders that held together only until a certain threshold was crossed. Maybe it was an object with embedded faults, stress lines that only snapped when heated from within. Or maybe, and this is where the imagination leaps a little, maybe K1 had experienced a history more extreme than most Oort cloud objects. A history that left it brittle, asymmetrical, ready to split in ways we haven't seen before. You know, when something lingers in the data like this, when it refuses to settle into the categories we've drawn for it, scientists feel a kind of quiet thrill because the universe is vast and the universe is subtle. And sometimes it takes a failure of prediction to point toward a deeper truth. And K1, in its strange delayed breakup, whispered that deeper truth. It suggested that even the smallest icy fragments drifting through space can challenge our understanding of physics, of formation, of cosmic history. We often imagine the solar system as a tidy place, but it's not tidy. It's full of leftovers, wanderers, surprises, and K1 ATLAS reminded us of that. But the story doesn't end with its breakup, because once those fragments began to drift, once they began to move in ways that defied simple gravitational modeling, astronomers started noticing something else, another layer of strangeness, another clue that the forces acting on K1 after fragmentation were not what we usually see. And that is where the mystery deepens, where the drift of the fragments begins to hint at forces beyond gravity alone, and where the next chapter of this story begins to open like a doorway into a wider puzzle, one that leads us from the breakup itself into the curious world of non-gravitational motion. Well, when we left K1 ATLAS drifting in the aftermath of its delayed and deeply puzzling breakup, the fragments were only beginning to tell their stranger stories. And you could almost imagine them whispering as they moved, whispering not just with light, but with motion, with the kind of motion that refuses to obey the clean lines Newton once traced across the heavens. Because when astronomers began to track those shards, one by one, hour by hour, they saw something that didn't quite add up. And, well, perhaps this is where the comet began to break, not only into pieces, but out of the boundaries of our expectations. It started with the drift. The first measurements came in within 24 hours of the fragmentation, and then more within 48 hours. And what surprised everyone was how quickly the fragments began to diverge from the gravitational path they should have followed. You see, gravity is usually the great conductor of celestial motion. It sets the rhythm and the pace. But comets, well, comets sometimes improvise. They release jets of gas, they shed dust, they produce little bursts of thrust as sunlight warms their newly exposed surfaces. And these forces, these small pushes, are what astronomers call non-gravitational effects. They're subtle most of the time, barely enough to nudge a trajectory. But K1's fragments showed something stronger. Not just stronger, but faster. Not just faster, but oddly directed, as if the comet had woken up from its breakup with impulses that refused to fade. And as the days passed, the smaller pieces drifted a few meters per second relative to one another, which may not sound like much, but in the cold, slow arithmetic of comet dynamics, it is astonishing. The angles at which they moved off course didn't match what you would expect from a cloud of debris, simply coasting away under gravity alone. And, well, the astronomers began asking themselves difficult questions. Was this just outgassing water and carbon monoxide vaporizing from fresh surfaces? Or was there something more layered inside those fragments, something that burned off differently, unevenly, with pulses of force that shifted their paths in ways too complicated for the usual models to handle? So the modeling teams they took the usual equations, the usual parameters for sublimation, spin, sunlight, and they tried to fit the motions of the fragments into curves that made sense. But the fits didn't settle. Some fragments drifted faster than predicted, others slower. Their inward and outward accelerations didn't synchronize with what a typical comet fragment might do. And that caused a kind of quiet panic in a few research groups, because outgassing can only do so much. If the forces were too large, then either the comet was made of something far more volatile than assumed, or, something else was acting on it. Of course, non-gravitational effects aren't new. You see, when 1I Oumuamua passed through the solar system in 2017, it displayed an anomalous acceleration that couldn't be explained purely by gravity, and astronomers tried to attribute that motion to outgassing, though no cometary coma was detected. Whether it came from trapped hydrogen or nitrogen, or whether it was something stranger, well, the debate still echoes. Then there was 2I Borisov, arriving from interstellar space like a classic comet, shedding dust and gas in ways we recognized, but even it needed non-gravitational tweaks to align the models with observation. And now 3I ATLAS, another interstellar visitor found by the same ATLAS survey network, showed its own flavor of odd motion, subtle but persistent, pressing against the assumptions astronomers used to shape their simulations. But K1 was different because it wasn't supposed to be interstellar. It wasn't supposed to behave like an outsider. It was catalogued as an Oort cloud object, a resident of our own solar system, a product of familiar processes. And when something from the Oort cloud behaves with the same strangeness as an interstellar object, that makes the scientific mind flinch. It makes you wonder whether classification is becoming slippery. It makes you wonder whether labels like native and visitor are not as distinct as we thought. The difficulty grew as the models attempted to account for the fragmentation itself. You see, once a single nucleus becomes many nuclei, the complexity multiplies. Different fragments spin at different rates. Different fragments expose different surfaces to sunlight, and each fragment releases gas differently from its siblings. And Um, well, these little aerodynamic differences in the vacuum of space act like miniature engines, engines you cannot map cleanly because they flicker on and off as the fragments rotate. The fragments of K1 weren't just drifting, they were jittering, accelerating, slowing, each with its own rhythm. And uh, that rhythm, that unpredictable dance, made even the most advanced non-gravitational models struggle. When astronomers plugged the data into their orbit determination software, the residuals were too large. The fits would not settle into clean curves. Every correction generated new deviations. Like trying to hold water in cupped hands, the predictions kept slipping away. It was then that scientists began to question the usual assumption that the sublimation came only from water and carbon monoxide. If the fragments contained other ices, perhaps ones with different vapor pressures, or if their surfaces were layered with porous materials that trap gases until they burst free in, sudden jets, then maybe that would explain the strength of the observed non-gravitational accelerations. But even then, the angles were peculiar. The thrust vectors didn't align with the sunlight direction in ways typical comets often do. It was as if the internal structure of each fragment was dictating the direction of the thrust rather than the sun alone. And you can almost imagine the scientists sitting at their desks late at night, staring at the residual plots, trying to convince themselves that this was just another case of complex but ultimately ordinary comet behavior. But the numbers kept saying no. The behavior kept saying no. The universe kept whispering no. It's not ordinary. It's not simple. It's not the way comets usually behave after breaking apart. Not just the speed, but the timing. Not just the timing, but the organization. Not just the organization, but the magnitude. And when multiple objects discovered in such a short time span by the same survey all show these odd deviations, the question becomes not whether it is coincidence, but whether we are seeing a pattern. So the scientists returned to the broader context. They recalled Oumuamua's acceleration without visible outgassing. They reconsidered 3I ATLAS and its need for complex non-gravitational modeling. And they held these beside K1's, drifting fragments, drifting faster than expected, drifting as though pushed by impulses that should not have been present. You see, when enough anomalies accumulate, something subtle shifts. The universe seems to lean in and ask, are you sure you understand what you're looking at? Are you sure the category you place this object in still holds? Because classifications are just guesses until the data makes them real. And with K1, the data kept arguing back. Some scientists speculated quietly that the comet's breakup revealed interior regions saturated with CO2 or other volatiles that sublimate explosively when exposed. But others wondered if the fragments themselves might be porous enough to trap heat, releasing it later in bursts that had nothing to do with the immediate solar radiation. And the more we explored those explanations, the more we realized how fragile and layered comet nuclei truly are, not just rubble piles, but thermal landscapes where heat migrates in unpredictable ways, building reservoirs of pressure before letting them go. Well, in those early days after the breakup, the data poured in from observatories on several continents. Each new measurement of a fragment's position hinted at acceleration components that varied over short intervals. A fragment would drift one way on one night, then slightly adjust the next, as though responding to internal engines flickering awake and asleep. And though the shifts were measured in meters per second, they carried profound implications. Because when you track a fragment across millions of kilometers. A slight shift here becomes a substantial deviation there. Comet modelers applied Monte Carlo simulations, generating thousands of potential outgassing patterns, but none matched the observations cleanly. So they began to relax the assumptions, allowing for sporadic jets, directional asymmetries, dust loading, variable conductivity inside the fragments. And even then, only partial matches emerged. It was as though each fragment was a world unto itself, governed by its own internal climate, responding to sunlight in ways we haven't yet learned to predict. You know, there is something strangely beautiful about this, something almost poetic, that these tiny shards of ancient ice, drifting across the void, have enough complexity to defy our equations. It's not out there, it's in here, in the nature of the material itself, in the billions of years of history locked within those frozen grains. And when we consider that fragments from K1 behave this way, we're invited to imagine how many other comets might contain hidden architectures we haven't yet glimpsed. And that leads us gently toward the next mystery. Because if the motion of K1's fragments refuses to fit our models, perhaps the reason lies not only in their structure or their dynamics, but in their chemistry. What if the non-gravitational forces are intertwined with what the comet is made of? What if the gas is released, the ice is exposed, the colors we see in its faint glow tell a deeper story? And this is where the journey naturally opens into the realm of spectra and color, into the hues that comets wear, like ancient signatures. Because as the fragments drifted and shimmered, astronomers began to notice something else emerging from K1 ATLAS, something about its light that was just as strange as its motion. Well, when astronomers first began noticing those shimmering drifts of the K1 fragments, they weren't just watching motion anymore, they were watching color. And that subtle shift in hue, that quiet golden tint emerging from the dust, pulled them toward a different kind of question. Because you see, light from a comet is not just light, it's a language, it's a whisper from the molecules dancing in its coma. And so when K1 began speaking in tones that did not match the standard lexicon of cometary chemistry, the scientists leaned in, eyes narrowed, trying to read meaning in every wavelength. Normally, when you look at a comet through a spectrograph, you expect certain signatures to appear, almost like old friends, the C2 emission bands, the CN lines, the faint but reliable signals from carbon chain molecules that paint most comets in that familiar bluish-green glow. The pattern is so well known that any deviation feels like a wrong note in a familiar melody. But K1 played a different tune. And, well, as soon as the first spectral readings came in, they saw something missing. It wasn't just lower in intensity, it was depleted. The carbon chain emissions were far weaker than expected, almost unnaturally quiet, like a violin that refuses to resonate even when the strings are pulled tight. That was the moment when chemists and dynamicists and observers all felt that shiver of curiosity pass between them. Because a carbon-depleted comet isn't unheard of, but it's rare. Not just rare, but unusual in exactly the way that invites questions. Questions about origin, questions about history, questions about what kinds of cosmic weather it might have endured. You see, carbon molecules are fragile, and they can be eroded, broken apart by ultraviolet radiation over long timescales. So a comet that lacks them might have been processed not just by the sun, but by the harsh fields of space between the stars. And here is where things become even more interesting, because K1's color was not simply muted, it was shifting toward yellow, a soft, dusty gold, almost like sunlight scattered through old parchment. And, um, well, that hue tells a story too. A story not just of chemistry, but of dust, a lot of dust. The kind of dust that dominates the coma when carbon emissions fall silent. The light we saw was sunlight bouncing off grains rather than the fluorescent glow of molecules. It means that dust was overwhelming the gas, tipping the balance, turning the usual spectral palette into something warm, something rare, something that made astronomers frown at their screens with a kind of delighted confusion. So, so why would K1 be so dust heavy? Why would its carbon molecules be so faint? Why would its glow lean toward yellow, a color that only a handful of comets in recorded history have shown with such clarity? The first hypothesis was simple enough. Maybe the comet was just old. Old in a way that baked out its carbon long before it fell inward toward our Sunday. Another possibility was that its surface had been heavily irradiated, chemically weathered, leaving behind material that refused to fluoresce in the usual way. And if that were true, it might connect K1 to a broader family of carbon-depleted comets that sit on the fringes of our understanding, but something didn't quite fit, not just with the carbon depletion, but with the timing. You see, K1 didn't show dramatic carbon signatures even before its breakup. And after the fragmentation, when fresh interior surfaces should have been exposed, the carbon lines still refused to brighten. That is odd, not just odd, but suggestive, as if the entire nucleus, top to bottom, surface to core, lacked the usual carbon-rich volatiles. And that kind of uniform depletion is hard to explain with ordinary solar system history alone. Then, as the comparisons rolled in, something else clicked into place. 3I ATLAS, the interstellar object found by the same survey in the same year, also showed chemical oddities. Not the same ones, but oddities nonetheless. Where K1 was carbon poor, 3I seemed unusually rich in CO2 relative to water. And that contrast formed a pattern that felt more like a theme than a coincidence. Both comets were outliers, both were chemically strange, both refused to fit the classical categories. And, well, that raised a whisper of a possibility that scientists rarely voice without caution. What if the chemical eccentricity of these objects is not random? What if we are beginning to see the edges of a population of bodies shaped in environments very different from our own? But before leaping outward to interstellar theories, astronomers turned inward, focusing first on the physics of how spectra are formed. You see, when a comet warms, its gases vaporize and fluoresce under sunlight. The color we see is not just beauty, it's a fingerprint. And when those fingerprints don't match, we are forced to ask deeper questions. Could the comet have formed in an unusually cold region of the Oort cloud where different volatiles froze out in unusual ratios? Could it have been exposed to cosmic rays for billions of years while drifting in the dark outskirts of the solar system? Or was it possible that K1 spent time not just at the edges of the system, but perhaps beyond them, that thought lingered, but scientists kept themselves grounded? Spectra do not prove origin, they only hint. And the hints, in K1's case, were tantalizing enough to keep observers awake late into the night. They knew that carbon-depleted comets exist within the solar system, though they are rare. But they also knew that the degree of depletion in K1 was unusually pronounced. And combined with its unusual breakup, unusual motion, and unusual behavior, it made the comet feel like a puzzle with pieces scattered across multiple disciplines. Well, one of the more intriguing ideas was that K1 might have gone through a thermal history unlike that of ordinary comets. If it had passed closer to stars before, or if it had been exposed to intense radiation in interstellar space, its surface chemistry could have been altered significantly. It's not out there, it's in here, inside the material itself, encoded in the bonds and breaks of molecules shaped over eons. And those altered surfaces could have influenced the gas release after fragmentation, contributing to the strange non-gravitational forces described earlier. But perhaps most striking of all was the way the yellow hue lingered. It didn't behave like a transient effect. It persisted even as dust dispersed, even as the fragments separated further. And that persistence implies that the dust grains themselves were unusual, maybe larger, maybe coated with materials that reflect light differently, maybe processed in ways we have not yet modeled. Dust like that can trace its origin back to conditions in planetary disks, in star-forming regions, in environments far colder or hotter than the ones that shaped typical Oort cloud bodies. So as the spectral data accumulated, astronomers began to compare K1 side by side with rare yellow comets of the past. Only a handful shared even a faint resemblance. Each of those comets had carried mysteries of their own, puzzles that were never fully solved. And now K1 sat with them in that small, uneasy category of chemical anomalies. And that made researchers wonder whether these yellow comets represent a distinct evolutionary history or perhaps a distinct region of formation. It's not that they suddenly declared K1 an interstellar object. Scientific caution prevents such leaps. But the comet's chemistry, alongside its structural and dynamic oddities, pushed the hypothesis from unlikely to plausible. The universe, after all, does not send messages in simple linear narratives. It sends them in light, in motion, in fragments of ice that break themselves open for us to read. And K1's broken pieces, glowing pale gold, seemed to be telling a story about its past, shaped by unfamiliar conditions. And there was one more thread in this chemical puzzle. When the fragments drifted further apart, astronomers expected some of the internal volatiles to express themselves differently. If carbon depletion had been only surface deep, the interior should have spoken clearly once exposed. But it didn't. The interior was as muted, as dust-dominated, as carbon-poor as the exterior. That continuity across depth hinted at uniformity in formation, not superficial processing. And that uniformity, again, aligned K1 with the idea of a comet formed in colder, more extreme, or more distant regions than most Oort cloud objects. The comparison with 3I ATLAS only deepened the intrigue. Two objects discovered by the same survey network in the same year, both chemically eccentric, both dynamically peculiar, both challenging our assumptions. It's not just coincidence, but also convergence. And whenever convergence appears in astronomy, it nudges the scientific imagination toward patterns, toward populations, toward the idea that our solar system is encountering more than just isolated anomalies. Perhaps it is sampling flavors of cometary chemistry drawn from reservoirs we have not yet catalogued. Well, you might say that the spectral lines were beginning to whisper the same message as the fragment drift. Something about K1 was fundamentally unusual. Something about its past left marks in its light, in its dust, in its missing carbon signatures. And you can almost imagine the comet speaking in two voices, one through motion and one through color, both telling us that we do not yet understand what shaped it. And uh, as we stand at this point in the story, with chemistry woven into dynamics and color woven into structure, there is a natural path forward. Because once astronomers understood that K1's composition was unusual, they turned their eyes towards something else. Not just what the comet was made of, but how its body was built. The shape of the fragments, the alignment, the structure of the nucleus revealed in its breakup, the very architecture of the comet began to matter. And that architecture carried its own mysteries, leading us onward, gently, inevitably, toward the question of how a nucleus could break apart into a chain so strangely ordered. Well, when we ended just a moment ago, K1 ATLAS was glowing in that strange yellow hush, its chemistry whispering that something about its past was not quite ordinary. And as astronomers stared at those drifting fragments, those little islands of ancient ice, they began to notice something else. Not just the chemistry, not just the color, but the shape of the breakup itself. Because you see, a comet's nucleus is supposed to be messy when it fractures, chaotic, a cloud, a spray. But K1 did something almost theatrical. It laid its pieces out in a line that stretched across the darkness with a kind of eerie neatness, as though the comet were revealing its structure not through randomness, but through choreography. Um, Imagine that for a moment. In the cold quiet of deep space, fragments that had no reason to obey anything but momentum arranged themselves with spacing that was strangely consistent. It was subtle at first, but the more images astronomers collected, the clearer it became. The pieces were not drifting in all directions, they were lining up, each fragment trailing a small coma of its own, like miniature ghosts of the original body. And beneath the leading fragment, that bright plume of dust and gas continued to shine like a natural jet, a headlamp cutting through the dark. That jet wasn't fading the way one might expect. It had persistence, structure, and an orientation that held steady for days. And that was not the signature of a simple crumble. So two schools of thought began to form, each trying to wrap itself around this quiet strangeness. The first was the natural rotation school. They imagined K1 spinning, rotating in such a way that stress built at the comet's midsection, peeling off layers like a potter's wheel flinging clay. And if the spin rate were high enough, if heat flowed unevenly, if the equatorial regions weakened first, then the nucleus could, in theory, shed pieces over time, each breaking free at intervals tied to the rotation period. That could create spacing, that could create a kind of order. It's not that the comet intended anything. It's that physics sometimes creates patterns that feel deliberate even when they're not. But the second school, the complex structure school, suspected something deeper. They saw in that alignment the possibility that the nucleus had never been a solid block at all. Instead, they imagined a rubble pile, a cluster of loosely bound boulders held together by gravity and ancient ice. A structure with seams and layers, with hidden planes of weakness, with blocks that could separate cleanly once a threshold was crossed. And this kind of nucleus doesn't peel. It cracks, it unlocks, it releases pieces that already existed as units before the breakup. The fragments don't need to scatter because they were siblings to begin with, quietly attached until the sun whispered too much heat into their bonds. Well, when astronomers compared the spacing of the fragments with their relative velocities, they found something curious. The distances between fragments were oddly compatible with a rotation period of a few hours. That is, if the comet spun once every few hours, pieces breaking free at successive intervals could naturally find themselves spread out in a loose line. But there was a complication. The orientation of the jet under the leading fragment didn't align elegantly with the expected rotational axis. And that inconsistency raised questions about whether rotation alone could explain everything. The jet seemed too consistent, too directional, as if powered by a pocket of volatile material that wasn't evenly distributed. And, well, this is where chemistry and structure intertwine. If the comet had layered strata regions rich in volatiles buried beneath tougher crust, then when those layers were exposed, they could unleash outgassing strong enough to act like propulsion, not just for the leading fragment, but for those behind it too. And that outgassing would push each fragment differently, depending on where its exposed surfaces were facing. So when astronomers noticed that some fragments were drifting more than others, the idea of layered internal complexity gained weight. It's not out there, it's in here, in the material itself, in the frozen landscapes hidden beneath the surface. You see, comets are not simple balls of ice. They are worlds in miniature, worlds with topography, fractures, fissures, voids, worlds shaped by billions of years of chemical weathering. If K1's nucleus contained ancient fractures filled with different ices, then when the sun warmed them unevenly, it could create bursts of activity that snapped the nucleus apart along predetermined lines. That would explain the clean edges some fragments displayed. It would explain the persistent jet. It would explain the spacing. But even this model struggled to explain the almost eerie order of the breakup. One possibility that scientists whispered about was that the comet might have been old. Not old in the ordinary sense, but structurally old, aged by radiation in ways that made its internal structure brittle. If the comet spent a great deal of time at the far edges of the solar system, or drifting between stars, cosmic rays could have altered its interior, making it more prone to crack into large coherent blocks rather than crumble into dust. And a nucleus like that doesn't break chaotically, it breaks geometrically. It breaks along seams shaped long before it ever entered our inner solar system. So with each hypothesis, scientists turned to the images, replaying the sequence of the fragments drifting apart, studying the way the leading fragment remained brightest. That brightness wasn't just a clue, it was a challenge. Why would one piece shine so consistently brighter than the rest? Some suspected it was simply larger, but the magnitude of the brightness suggested something more active. A jet, a vent, a source of gas that kept expelling material even as the fragment cooled. And that source could have been hidden beneath layers of crust, dormant for billions of years, awakened only when the breakup exposed it to the sun for the first time. The more scientists debated, the clearer it became that no single explanation quite fit. Rotation fit part of the story, but not all. A rubble pile structure explained the uniformity of the fragments, but didn't neatly account for the continuous jet. Layered volatiles matched the outgassing, but not the spacing. And that interplay of partial truths, that tension between models, is exactly where science thrives. Because when data resists simplicity, it pushes us to expand our understanding rather than shrink the universe down to what we already know. Well, one particularly fascinating idea emerged from considering the thermal history of K1. If the comet had multiple layers of ices, with different sublimation points. Exposure of deeper layers after the breakup could have created short-lived engines beneath the fragments. Those engines would push the pieces into alignment, not through intention, but through physics. And uh, we, we, they often imagine comets as passive wanderers, but they're anything but passive. They're dynamic, they're reactive. They respond to sunlight like sleeping creatures stirring from hibernation, each layer of their structure awakening at its own speed. So, so the alignment of the fragments began to feel less like coincidence and more like a window into the internal architecture of the nucleus. A comet that breaks into evenly spaced segments, each with its own coma, each drifting with its own character, is telling us something intimate about how it was built. It's telling us that the nucleus wasn't a uniform block. It's telling us that gravitational packing, thermal fractures, and ancient layering sculpted a structure that could survive billions of years intact, only to reveal itself piece by piece in the warmth of a single solar encounter. And that brings us to a deeper question. If K1's structure is so unusual, if its nucleus behaves unlike the classical comets we've catalogued for centuries, then what does that say about its origin? Was it shaped in the Oort cloud like the others? Or was it shaped somewhere else? Somewhere colder, somewhere harsher? Somewhere where materials fuse differently, where dust grains accrete under conditions we haven't fully modeled. And that leap of imagination begins to point toward the possibility that K1 might not be a typical Oort cloud comet at all. It might be something else, something from farther away, something that carries the structural fingerprints of a different birthplace. And that thought, that whisper of connection between structure and origin naturally leads us toward the next puzzle. Because just as K1 reveals its inner architecture through its breakup, another object found in the same year, 3I ATLAS, reveals its strangeness through its interstellar motion. And when two objects discovered by the same survey begin to echo one another in odd ways, scientists can't help but wonder whether these two might be connected, not just in timing, but in nature, not just as coincidences, but also as clues. And so the question begins to take shape. Are K1 ATLAS and 3I ATLAS truly strangers, or are they a kind of cosmic pair? A pair that forces us to look at the boundaries between our solar system and the vast wandering populations beyond it. And that is where our journey turns next, toward the strange idea that K1 ATLAS might have a twin. Well, when we left the story hanging on that quiet suggestion that K1 ATLAS might not be wandering alone in its strangeness, the natural next step was to turn our gaze toward its so-called twin 3I ATLAS. And even calling them twins feels a little mischievous, because they don't look alike, they don't move alike, they don't break alike, but there is that unmistakable echo between them, a resonance in their oddities, a kind of cosmic rhyme. So let's drift into that question together, slowly, the way one might approach a dim light on a distant ridge, unsure whether it's a star or a lantern left behind by another traveler. You see, in the same year, 2025 ATLAS, that sky-scanning sentinel in Chile and Hawaii caught two objects that behaved in ways astronomers weren't prepared for. And the quiet coincidence of timing alone would have raised eyebrows. But it wasn't just timing, it was temperament. Each of these visitors refused to conform to the rules their categories were supposed to follow. 3I ATLAS arrived from interstellar space. Its orbit unmistakably hyperbolic. That long sweeping curve that says this thing does not belong to the Sunday. And K1 ATLAS, though labelled as Oort cloud in origin, behaved chemically like a stranger, structurally like a stranger, dynamically like a stranger. Two objects, two outliers, both caught by the same system, both carrying signatures of being different. Well, the mind begins to wonder, doesn't it? Not just about the objects themselves, but about what it means for them to appear together. Are we watching the universe throw in a pair, almost as if to say, here, look again, look closer? That quiet question lingered among astronomers. And something about the way K1 cracked into near equal space fragments reminded them of interstellar debris models, the kind that simulate how loose rubble piles from distant planetary systems might behave when they encounter new stars. And the color of K1, that dusty yellow, that rare depleted carbon signature, whispered yet another parallel. Because interstellar space is harsh. It strips, it erodes, it recycles. And when you see a body with surface materials that look weathered by something older than the sun, you begin to lean in that direction. But let's not leap too quickly. Scientists, after all, don't leap. They tiptoe, they hesitate, they compare what is with what might be. And they first ask the simplest question: could K1 ATLAS and 3I ATLAS be related at all? Not just metaphorically, but literally. Could they have once been part of the same greater body? Could they have shared a birthplace before their paths diverged in the vastness between stars? It sounds dramatic, almost mythic, but when you're dealing with objects that wander for millions or billions of years, history stretches enough to make improbable things possible. If a larger progenitor body were disrupted near another star, fragments could drift independently until some of them found their way toward our Sunday. And if two such fragments happened to reach us in the same era, it would feel miraculous, but not unthinkable. The galaxy's big, but it's also full of currents we barely understand. Still, the orbital data complicates this idea. 3I ATLAS approached on a clearly interstellar trajectory. K1 ATLAS's orbit, while long period, is compatible with an origin within the Oort cloud. If the two shared a parent, you would expect their trajectories to echo one another more closely. But science is not just about which box an object falls into. It's about how much uncertainty you're willing to entertain. The Oort cloud itself is not a sealed vault. It may contain captured interstellar objects, bodies that wandered too close and were gently nudged into orbit around the Sunday. So if K1 were captured long ago, its orbit might masquerade as native, even if its chemistry and structure betray a more distant origin. And then comes the second scenario, one favored by many cautious astronomers, that the two are not related at all. The Atlas simply had a particularly lucky year, catching two rare outliers, because its sensitivity and cadence had improved enough to reveal things we used to overlook. In this view, K1 and 3I belonged to completely separate populations. One is a strange Oort cloud object shaped by exotic thermal histories. The other is a genuine interstellar traveler. The similarity is illusion, coincidence. The universe's version of two unfamiliar faces appearing in the same crowd and making you think they might be siblings. But there is a third idea, a kind of middle road, that grips the imagination more tightly than either extreme. What if K1 is not directly related to 3I, but both are part of a larger trend? What if what we're seeing is not two siblings, but the first two members of a family we've only now begun to notice? That, that possibility is what makes astronomers sit back, breathe out slowly, and glance at the sky as though it is suddenly more crowded than before. Because the Atlas network and similar all-sky surveys are becoming more sensitive. They're finding dimmer objects, stranger ones, faster ones. What if there is an entire category of bodies, chemically odd, dynamically unpredictable, passing through the solar system regularly, and we've only now started to see them? And that possibility isn't just poetic, it's statistical. The more we look, the more anomalies we find. And the more anomalies we find, the less anomalous they become. It's not just coincidence, but also inevitability. Perhaps K1 and 3I are ambassadors of a hidden population that has always skirted the edges of our detection. Bodies formed around other stars, shaped by alien heat, alien cold, alien chemistry, drifting between systems like dandelion seeds on a galactic breeze. But let's step back again. Let's imagine what it would mean if K1 and 3I were related in some deeper way. Perhaps they were formed in the same distant stellar nursery. Perhaps they were once fragments of a scattered protoplanetary disk that was disrupted when its star migrated through dense interstellar regions. So across time, they drifted, battered by cosmic rays, losing carbon, gaining fractures, aging in the kind of deep cold that thickens crusts and alters reflection. If that were true, then their arrival in the same year wouldn't be magical coincidence. It would be a statistical echo of a shared past. Well, scientists didn't stop at philosophical speculation. They began to build models. They compared the CO2 to H2O ratios in 3I. They compared the carbon depletion and chromatic dust behavior of K1. They looked for patterns in known carbon-depleted comets, hoping to see if these objects aligned with any group within our own system. And what they found was both reassuring and unsettling. There are carbon-depleted comets here, comets that seem native but behave strangely. But none show the combined profile of K1, and none share the chemical equilibrium seen in 3I. So, if these two comets belong to any known category, it is a category with no other members yet found. The more astronomers stared at the data, the more they began to consider the capture hypothesis again. What if the Oort cloud is not exclusively native? What if it acts as a kind of cosmic harbour, gathering not just refugees from the early solar system, but travellers from beyond? Some objects might enter slow slightly under the sun's distant pull and become long-term residents without ever revealing their true origins, unless something like a close perihelion pass breaks them open. And K1, in its dramatic fragmentation, may have done exactly that. It may have exposed an interstellar heart beneath a deceptively native orbit. Of course, even if that were true, it would not guarantee a connection to 3I, but 3I provides a necessary context. Before 2017, before Oumuamua, before Borisov, we had no confirmed interstellar visitors. Now, within a handful of years, we have multiple. And in 2025, ATLAS detected 2 anomalies in quick succession. And, when the same instrument catches 2 rare types of strange objects, it naturally encourages comparative thinking, comparative reasoning, comparative wonder. And that wonder extends beyond their chemistry and orbits. It reaches into the philosophical heart of astronomy. What does it mean for our solar system to be porous? What does it mean for material from other stars to drift among our planets, our dust, our light? It means the galaxy is far more interconnected than we used to imagine. It means the boundaries we draw around our system are not walls, but membranes, soft, permeable, alive with exchange. And so the question of whether K1 and 3i are related transforms. It becomes less about lineage and more about landscape. Not whether they came from the same parent body, but whether they came from the same cosmic culture, the same class of environments, the same families of icy wanderers, forged under foreign suns. If they did, even loosely, then their appearance together is not coincidence, it is revelation. Well, the scientists working on long-term orbital integration have begun testing reverse trajectories for K1, pushing simulations back millions of years to see whether its path ever resembled something interstellar. But the chaos of fragmentary motion makes these reconstructions difficult. Tiny non-gravitational forces early in its journey could have changed everything, and the farther back you push the model, the blurrier the path becomes. You lose the thread, you lose the certainty. The trail dissolves into a haze of probabilities. But that haze is where new discovery lives. It's not out there, it's in here. In the models we build, the data we refine, the questions we're willing to ask. And one day, when more objects like these are discovered, and they will be discovered, patterns may become clear enough to unravel the mystery. So let's think of K1 and 3i not as identical twins, but as cosmic siblings who carry different memories of similar origins. One arrived intact, interstellar, fresh and strange. The other may have been captured long ago, reshaped by our sun, fractured open only now to show us what it once was. And that brings us toward a broader horizon. Because if these two objects hint at a larger population of unusual wanderers, then our surveys, our telescopes, our instruments are on the cusp of seeing a new layer of reality. A layer in which anomalies become clues, and clues become patterns, and patterns become new models of how the galaxy shares its debris. And it is exactly this possibility, this idea that the strange may become routine, that leads us naturally toward the next chapter. A chapter where we step back from specific objects and look at the entire future of sky surveys, the future of discovery, the future of recognizing that what once seemed rare might soon become normal. Well, when we left off, the idea was beginning to take shape that K1 ATLAS and 3i ATLAS might be more than isolated curiosities. They might be signals, faint and flickering, of a broader transformation in how we observe the sky. And if that's true, then the real story isn't just about two strange visitors. It's about the instruments, the surveys, the eyes we build to watch the heavens, and how those eyes are changing what we believe is normal. Because you see, the sky has always been full of oddities. It's we who have only recently become capable of noticing them. This is the quiet revolution of the all-sky era. Networks like Atlas, Pan-STARRS, and soon the Vera Rubin Observatory are sweeping the sky, not just once a night, but again and again, building a living map of what changes, what drifts, what brightens, what dies. And, in that map, the strange becomes visible, the faint becomes familiar, the improbable becomes routine. It's not out there, it's in here, in the sensitivity of the detectors, in the cadence of the scans, in the algorithms that sift through millions of blinking points. So when K1 fractured into its golden chain of fragments, and when 3i arrived with its exaggerated CO2 signature, the fact that we noticed them at all wasn't just luck. It was design. It was capability. It was the new age of astronomy quietly proving itself. And uh, as these networks expand, as their cadence increases, we can expect the catalogue of strange objects to grow. Not just comets behaving badly, but asteroids behaving oddly, interstellar fragments slipping through the solar system like seeds on the wind, and even things that don't have stable categories yet, things we don't have names for. Well, that shift forces scientists to rethink what counts as anomaly. If an object like K1 had appeared in the 1900s, it might have been dismissed as observational error. If 3I had been spotted in the early 2000s, its interstellar nature might have remained undetected. But now, with all sky surveys comparing nightly data against decades of baselines, every deviation stands out as a story. And that means more stories, more puzzles, more drifting shards of the unexpected. One of the most important tasks moving forward is tracking K1's fragments over the long term. They may fade quickly, swallowed by distance and dust, but the subtle fingerprints of their orbits can reveal whether the non-gravitational impulses they experienced continue to change their paths in measurable ways. And that matters because the persistence of those forces can tell us whether the deeper layers of the comet were rich in volatiles, or whether the breakup exposed nothing more than inert rubble. It can even hint at whether the nucleus had internal cavities, or clustered masses, or regions of exotic ices. So the observations cannot stop at fragmentation. They must continue night after night, even as the fragments dim beyond easy sight. And this is where the modern sky surveys excel. ATLAS may detect the early motions, but deeper follow-up from Rubin, from Subaru, from large infrared telescopes can push the data further. Each shift in position, each faint glimmer of activity becomes part of a mosaic that tells the story of how a comet's insides behave after being ripped open by the sundae. But K1 is just one thread. And surveys of the future will not only track individual fragments, but build statistical groups of similar objects. What if there are dozens of carbon-depleted comets lurking in the faint end of the catalogue, waiting to be recognized as a family? What if there are other objects that show unusual non-gravitational accelerations, hinting at complex internal structures? What if there are objects captured long ago from interstellar space that have been masquerading as Oort cloud natives for eons? The only way to know is to gather enough data that the anomalies themselves reveal symmetry, patterns, histories. And then there is the spectral side of this revolution. When the James Webb Space Telescope turns its deep infrared eye toward comets, it is able to read not just their colors, but their temperatures, their dust sizes, their molecular fingerprints. And, combining Webb spectra with ground-based optical surveys is like listening to two instruments in harmony. One hears the high notes, the fluorescence, the gases. The other hears the bass tones, the dust, the warmth, the structure. Together, they create a three-dimensional profile of what a comet truly is. So imagine this future scene. A dim object appears in ATLAS, drifting across the sky with a strange acceleration. Within hours, Pan-STARRS confirms motion inconsistent with pure gravity. By the next night, Rubin's deep exposures reveal faint jets. Webb follows days later with spectral lines unlike any catalogued comet. The object does not need to be bright. It does not need to be dramatic. It only needs to be there. And we will see it. We will know it. We will understand that it does not belong to the old categories. And when such detections become frequent, the meaning of anomaly will change. We may begin to classify comets not by their orbits alone, but by their chemical clans, their structural families, their fragmentary behavior. It's not just long period or short period anymore. It's fragile layered bodies, it's carbon depleted objects, it's CO2 rich interstellar travelers, it's dynamically hyperactive fragments, each category expanding as more examples drift into the frame. Well, astronomers already know that every deviation from prediction is a doorway. When an object defies its trajectory, it invites new physics. When a spectrum defies its expected lines, it invites new chemistry. When a nucleus fractures in strange, almost geometric ways, it invites new structural models. And that is the heart of scientific progress. A small thing behaving unexpectedly, forcing a large theory to stretch. K1 is a reminder of that. So is 3I, so is Oumuamua, so is Borisov. Each one is a quiet tap on the shoulder, a suggestion that the solar system is not an isolated island, but part of a cosmic ocean with currents we are only beginning to map. And that ocean is getting brighter, because as our instruments sharpen, as our surveys multiply, the faint becomes loud, the rare becomes common, the unseen becomes ordinary. A century ago, interstellar objects were speculation. Now they appear before our telescopes with regularity. A decade ago, a comet like K1 might have been lost in noise. Now it is a subject of deep study. So the future of skywatching is not just discovery, it's humility. It's recognizing that the universe is more crowded, more varied, more intricate than we believed. It's remembering that the pathways between stars are not empty, but full of stones and dust and fragments carrying the histories of alien worlds. And that's the thing. As these strange objects accumulate in our catalogues, we begin not just to observe them, but to understand our place among them. We grow older, clocks tick, and our instruments grow sharper, and the sky keeps sending us these quiet messages, asking whether we're ready to listen. And as we listen, the final thread of this story comes into view. Because now that we've explored K1's breakup, its motion, its chemistry, its structure, and its possible relationship with interstellar visitors, we arrive at the question that sits beneath everything. Not just what K1 is, but what it means. And that is the question that opens the final chapter, the one where these small drifting shards start telling us something vast about our own cosmic origins. Well, when we paused just a moment ago, we were standing on the edge of a thought, a kind of quiet threshold where the science of K1 ATLAS stops being only about ice and fragments and numbers and begins to become something softer, something more human. And that's the thing, isn't it? These little shards of frozen dust drifting through the night sky, they shouldn't matter. They're tiny, they're fragile, they're simple, but somehow, through their strange behavior and their quiet defiance of our expectations, they end up telling us something large, something vast about who we are and where we fit into the story of the universe. So let's breathe into that for a moment. Let's take everything we've traveled through together. The delayed breakup after perihelion, the odd accelerations that seemed to ignore Newton's careful handwriting, the unusual chemistry that muted the carbon chains into silence, the unexpected golden glow, the structured alignment of fragments, the possible kinship, thin but persistent, between K1 and its interstellar counterpart 3I ATLAS. It all forms a chain, doesn't it? Much like the fragments themselves, one piece leading into another, each held in tension by the questions we still cannot answer. And, well, Maybe that's why the story of K1 feels so strangely important. Not because it is the biggest comet, not because it is the brightest, but because it is the kind of object that reminds us science is not a catalogue of certainties. Science is a trail of crumbs, a whisper, a pattern in the dark. And when a comet like K1 refuses to behave, it forces us to widen our map, to redraw our boundaries, to rethink what counts as typical in a universe that has never cared much for the word typical. You know, when astronomers speak about anomalies, they often do it with a kind of quiet reverence. That slight tremble of curiosity in their voice, because anomalies are the moments when the universe leans down and taps us on the shoulder. It's not saying we were wrong, it's saying look again, look deeper, look with the kind of attention that turns confusion into discovery. And K1, well, it really is one of those taps on the shoulder, a comet that survived the sun's heat only to break afterward when the danger should have passed. A comet with fragments that refused to scatter and instead aligned like pearls on a cosmic string. A comet whose chemistry spoke in unfamiliar tones, whose behavior rhymed faintly with interstellar visitors, whose presence arrived in the same year as 3I ATLAS, as if to say that the universe is sending messages not singly, but in pairs. So, what does it mean, then, to bring this story toward a close? Not an end, because nothing in the universe ends cleanly, but a kind of soft landing, a gentle slowing, like a spacecraft approaching a silent world. Perhaps the best place to finish is where all scientific stories eventually return to perspective. Um, from this little rocky planet, we look outward, we watch ice and dust dance in the sunlight millions of kilometers away. We chart their trajectories, measure their spectra, argue about their composition. But beneath all that, beneath the models and the data and the diagrams, there is something else happening. Something older, something quieter, a kind of listening. We are a species that listens to the universe, not just with ears, but with equations, with mirrors, with algorithms. We listen because the universe is telling a story, and every once in a while, a visitor like K1 ATLAS drifts past and opens a chapter we didn't know existed. Well, when we watch a comet break in slow motion, when we watch its fragments drift like tiny lanterns across the darkness, we're not just learning about thermal stress or rotational fracturing. We're learning about time, about patience, about the way cosmic history is written in layers of dust so thin and delicate that only sunlight can reveal them. We grow older, clocks tick, and yet these comets carry memories older than any of us, older than any civilization, older than the Earth's mountains and rivers. And that's why studying them feels strangely intimate. It's not out there, it's in here, in the questions they ask of us. Questions about origin, about migration, about the strange ways different worlds leave fingerprints on the materials they shed into space. K1 ATLAS, with its muted carbon and golden dust, may carry the chemical aftertaste of environments we have never seen. 3I ATLAS, with its CO2-rich signature, may carry the thermal imprint of a star whose warmth is not the sun's. And together, together, they remind us that the solar system is not a closed box, but a crossroads. So, what happens next? What happens after this chapter? Astronomers will continue following K1's fragments until they fade. They will feed the spectral data into models, searching for the subtle ratios that reveal formation temperatures. They will refine the non-gravitational parameters, testing whether the accelerations match known outgassing profiles or something stranger. They will compare its behavior to every carbon-depleted comet in the archives and every interstellar visitor discovered so far. And this is the heart of the scientific process. Piece by piece, uncertainty narrows, not in a straight line, but in spirals, not in leaps, but in gentle adjustments where each new observation shifts the story a little closer to clarity. But here's the thing. Well, here's the quiet truth lurking beneath it all. K1 ATLAS may be just the beginning, because as the surveys watching our sky become more sensitive, as the Rubin Observatory begins its relentless nightly sweep, as machine learning scours patterns our eyes might miss, the number of unusual objects we discover will rise, the exceptions will multiply, the anomalies will become familiar. And one day soon, we may look back at 2025 and realize it was the year we first glimpsed a population of objects that had been hiding in plain sight all along. Imagine that, a future where interstellar visitors pass through our catalogues not as rare wonders, but as routine guests. A future where comets with chemistry shaped by alien suns drift past our world like pages torn from distant stories. A future where the solar system is recognized not as a lonely island, but as a port where travelers occasionally stop, break, glow, and continue onward. It is a humbling idea. It's not just about comets. It's about connection, about the threads that tie star systems together, however loosely, across unimaginable space. And perhaps that's the real meaning behind K1's appearance. Perhaps its golden glow, its unusual structure, its companion discovery in 3i ATLAS are all quiet reminders that the universe is dynamic, fluid, migratory, that nothing stays where it began, that even fragments of ice can wander for billions of years and still find themselves illuminated by an unfamiliar sun. So as we bring this narrative toward its resting place, let's hold on to that sense of wonder, that feeling that we are witnesses to something larger than the data alone. The feeling that comets, in their fragile silence, are storytellers. They tell us about the youth of planetary systems. They tell us about the violence that tears worlds apart. They tell us about chemistry shaped in darkness and dust shaped in starlight. And sometimes, if we're fortunate enough to catch them at the right moment, they tell us something about ourselves. Well, that moment is now, because every time we track one of these strange visitors across the star-swept dome of the sky, we become part of the story too, not just observers, but participants in the ancient dialogue between matter and meaning. And so the question we leave with is not simply what K1 ATLAS truly is, or whether it's interstellar or merely unusual, or whether it is kin to 3i ATLAS. The deeper question is what these small icy wanderers reveal about the nature of cosmic history and our place within it. And that is exactly where the next chapter will take us, into the wider mystery of how the universe shapes its small drifting fragments, and how those fragments in turn shape the way we see the universe. Because the story isn't ending here, not at all. It's only beginning to open.